Control Option Command H. I do not like that. All right. Okay, now I am recording. All right. Any guesses for B? Does someone want to read me their sentence? Go for it.
That for every student, there's this at least one course and one grade.
Mm-hmm. Yeah, so for every student, there exists at least one course and one grade. Yeah. Which is correct. Like that's a valid way of reading this. I would maybe take it the next step and put it into more natural language of each student took at least one course and received a grade. Right. And that's more clear to like us as humans, where so we go back to pen. So every student that gets the for all part of it took at least one course and received a grade. You can add like all the details of like in fall semester at Acme University. But yeah. And so because we don't have any actual information that goes into these variables, right? It's just general. And so we have to make a general statement as a result. What about C? Someone want to read me their sentence for C? Yeah.
I always said for all courses, there exists a student who got an F.
Yeah, for all courses, there exists a student who got an F. And so yeah, so taking it the next step for that one, we could say every course had at least one student who failed. Right? And so we have that universal quantifier for every course. And there exists at least one student who received a grade of F. All right. And so it's interesting because these are now swapped. So what is D saying then? Yeah.
There exists one class for every student. Okay.
There exists one class, at least one class, where every student got an A. So does that mean that like, I don't know the course numbers for seminar anymore, since they changed it, but like the first seminar class, is that, if I said that every student got an A in seminar 1, I would argue that that fulfills what you said, but is that what is represented in the statement? Yeah.
Is it for all students that exists a course where they got an A? Like for every student, they at least got an A in four.
Yeah. And I think, yeah. And so the thing is, like, we don't want to say that there exists one course that every student took and every student got an A in. That's different from saying, like, every student took a course. Like, every student took at least one course where they received an A. And that's different where, like, one student took a seminar class, one student took a history class, and they each received an A in one of those, as opposed to they all took this class and they all received A. So yeah, so each student took at least one course where they received an A. So yeah, and like there's a little bit of nuance here as we're trying to translate these logical statements into natural language. But yeah, that would be my attempt at this. Any questions? Okay. All right, so our goal for today, we're going to go over a little bit of 4.4, and then we're going to look at 4.5. 4.4's goal is to write arguments and symbols. And then 4.5 is this is the thing we've been building up to, which is how do we prove things and like formally learn these methods of proof. So for 4.4, we've got an example of tonight. Let's see. The name of this person is Gottlob. Will study, or he will watch a movie. So that's statement one. And then statement two is if Gottlob does not have a test tomorrow, then he will not study tonight. So if no test tomorrow, then he's not going to study tonight. And our third statement is that he does not have a test tomorrow. And then we conclude that therefore Gottlob will watch a movie tonight. So this is an argument that we're making, right? We start somewhere, we make some statements, we end somewhere. The structure of this is we have this conjecture, which is something that like we think is true. So we've got an idea, but we don't know whether or not it's actually true. We have to be able to prove it. And so we start with a hypothesis or multiple hypotheses or premises. And then we've got some arguments to get us from point A to point B. And then we have a conclusion. And then once we have our conclusion, if we have successfully proven it, then we get a theorem. Some things we don't prove, like the axioms, which is those are the big things that we assume, and then from there you so you assume the axioms are true and you prove everything else. One of the best examples of this is in the math department, there's a course called real analysis. It used to be advanced calculus, but it's the same thing. And it's a process of we start with these axioms and you essentially prove theorems until you build up to the stuff that you learn in Calc 1 of like, here's how to do this derivative rule. And like, here's the equation for a derivative. You prove that. Like you work with super small things and then you build up until, oh, I have this theorem. Hooray. Uh, that was one of my favorite classes as a student. And it's all about this sort of format where we prove things, we have hypotheses using the things that we assume to be true or know to be true, and then we prove theorems and then use that theorem and prove other stuff. So it's all this way of just like thinking logically and building up an argument as you go. Okay, so for this example, we've got sort of how many? So let's underline. So there's different conditions of what Gottlob will do. So either Gottlob will study or he will watch a movie. And then there's this condition of he does not have a test tomorrow. And then he will not study tonight. And so since there's a not in there, we'll say that that's a not P. And then we have a statement that Gottlob does not have a test tomorrow. And so that's not R. And then we say, therefore, you will watch a movie tonight. And that was yeah.
Does not have a test tomorrow is R. Does not have a test tomorrow is not R.
Yeah, so I think it should be not R.
Oh.
So if R is Gottlob has a test tomorrow,
Mhm.
then Gottlob does not have a test tomorrow is not R. Thank you for catching that. All right, so these are all, that's all fine and good. We're practiced at this. We're picking apart a sentence into its variables. And so let's write it. And I might scroll back and forth to get everything. So P is, I've already forgotten it. P is he will study. Q is he will watch a movie. R is he has a test tomorrow. So P is study. Will study. And then Q is watch a movie. R has test tomorrow. And so we start off with he will study or he will watch a movie. So that's P or Q to write that in symbols. And then if Gottlob does not have a test tomorrow, so if he does not have a test tomorrow, then he will not study tonight. So we've got the then, and then he will not study. So not R implies not P. And then the statement that he does not have a test tomorrow, and so that's not R. And then, therefore, he will watch a movie tonight. And so this forms this kind of logical equation, kind of like, you know, how you write like 13 plus 29, like when you're learning arithmetic, you kind of write it like that. We've written some logical statements in symbols, and it looks kind of like when we do addition or subtraction or multiplication. And so now we've represented this argument symbolically. I don't want to spend a ton of time on this. I think it's super cool. But now we have this written in symbols, and we want to be able to find out, like, is this argument valid? And so I won't write it out, but this is all, we're trying to go from here to our conclusion. And with that, if we assume that like the operator, so like over here with addition, the operator is plus. And so if we assume that the operator is and for each row, we want to find out that P or Q and not R implies not P and not R. And we want to find that all of that concludes us to Q. So that's a big implication. Not big as in like intimidating. It's just like fairly long and a little bit complicated. But we know how to break down complicated things, right? If we say that all of this is some expression, we'll call it D or give it a letter. And if we can solve all of these individual things that give us the truth value of D, then it's a matter of solving D implies Q. And if we do that, then we're good. And so the book, let's go to the book. Let's see, this is on page 84. And so, right, we could spend time and write all of those out for P, Q, and R. And then we solve each of the propositions. So P or Q, not R, not P, not R implies not P. And then if we have D, B, we've ANDed all those together, then we can calculate what's the truth value of D. And then we use our implication rules to give us D implies Q, right? Looks complicated, but it's just a little bit of tedious work, and then we can get to our conclusion. This ends up being a tautology, and so then we can say that this is in fact a logical argument. So we can write these arguments in symbols and then write out our truth tables and be like, here, we did it. Unfortunately, or maybe fortunately, depending on your point of view, we don't do this to prove things a lot. We could, but we don't, because writing truth tables is tedious, and I don't know, I prefer words. I will mention, I think this is pretty cool, where we've got these so-called rules of inference, where we have sort of these forms of how a logical argument could be structured, where we say something like, here is our statement P, then we say P implies Q, and then we infer Q. This is something called modus ponens. Ponens means affirms. So basically we say, if we assume P and then we assume P implies Q, then we get Q. Right? So the moon is visible. If the moon is visible, then it is nighttime. Therefore, and then if the moon, so hold on. If the moon is visible, then it is nighttime. That's this statement. And then we say the moon is visible. And then we would infer, then it must be nighttime. There's also modus tollens. Tollens means denies, where we assume that Q is not true, and then we state the implication P implies Q, and from there we infer that Q or that P must not be true. And so again, this is an equation that we just and each of the lines together, and then we get the implication. There's conjunctive simplification. And so we get P and Q implies P. This is fairly simple because we have like, what was this? Yeah, like if I want coffee and I want tea, therefore I want coffee. Like, yeah, obviously. Conjunctive in this case means and so it's a simplification where like I want coffee and I want tea, therefore I want coffee. So I've simplified my conclusion a little bit. If we have something like P or Q, and then we assume not P, this is a disjunctive syllogism, just disjunctive because we have an or in there. And then the hypothetical syllogism is we have two implications, and so we're trying to prove the transitive property. Yeah, we're not going to go too much into this. I thought it was cool. There's a lot of practice in the book in the examples in 4.4, so like page 88 and 89, like identifying the rules, like is it valid? The other thing I want to mention from this section is, where'd you go? Here it is. This is where we get the idea of logical fallacies. So like you learn them in English class in high school. But there's a fallacy like when we affirm the conclusion, where if we say P implies Q, and therefore P implies Q and Q, therefore we can conclude P. But that's a fallacy because we can't do that. Just assuming Q doesn't give us information to go backwards. And then denying the hypothesis, which is if we assume that there's an implication, P implies Q, and we assume that the hypothesis is not true, that doesn't necessarily give us that the conclusion is not true as well. So that's denying the hypothesis. Again, it's a lot of symbols, so I expect it to not make much sense. I just wanted to make you aware. I think this is pretty cool. It's like math, but for logic. This is actually, do I still have that window open? No, I don't. Give me a second. So like this sort of stuff that we're talking about is propositional logic or like propositional calculus. And this is like a whole area of study. And if you're in computer systems right now, this should also feel similar, where like you're getting into not and or and exclusive or. And so it's the same kind of idea where you start with these basic building blocks and build yourself up to this complex logical world, which I think is pretty cool. All right. Let's talk about methods of proof. Okay, so essentially there's two kinds of proofs. We have direct proof and indirect proof. We just talked about how we can like represent things in symbols. And so you can do that if that's helpful for you to kind of break down a sentence to say, this is P, this is Q, I am saying Q and P or Q or P or whatever applies to that situation. You can break it down in symbols if that helps your brain make sense of this natural language that you're given. But the goal of the proof is to write things in natural language. There's a sentence in the book which I want to read to you, which is, a well-written proof is most often presented in paragraph form, using complete sentences with sufficient justification and explanation given for the reader to follow, but not so much as to be laborious. And so this is kind of where proof writing, and like this is the heart of mathematics, of logical reasoning, where we want to, it's not so much I'm writing algebra, but it becomes more of like a writing task. So for example, if you're writing proofs, maybe you could like take it to the writing center and walk it through with the tutor there to say, this is what I'm trying to prove. Like, does this argument flow? And it becomes more of like a writing a creative task where it's more of an art than, oh, there's like one exact answer. The exact answer is being able to prove something, but there's different ways to be able to get there. There's different methods of proof that you can employ. There's different writing styles that you may use that someone else doesn't use. And so this is where it kind of like will provide the guidelines and boundaries, and then from there it's kind of up to you. So with simple proofs, it'll be fairly similar, but if we get into more complex things, then it can be different. I remember in grad school, we'll talk about like these types of proofs, but there is a case where I was working with partners trying to prove something, and my partners were like, this type of proof works, and like we only want to use this type of proof. And I'm like, I can see a direct proof and I think it works. And so like we clashed a little bit of there's different ways to get there. And so it's just reconciling, like in our group, which do we think is the most convincing argument? Okay. The other thing the book has in this, I really encourage you to read through. This is page 91, where this section starts. I really encourage you to read through at least the introduction section. I think it does it really well. It talks about how like examples are insufficient, which we've discussed. And then you can use variables to represent things. You can provide justification for each step, and then so on. Okay, so we'll talk about direct proof first. There are two types of indirect proofs, which we'll go over at the moment. There's proof by contradiction. That's supposed to be a T. Let me rewrite that. And then proof by contrapositive. So essentially three, directly and indirectly. And so we still have this idea where we have a hypothesis, and then we have some arguments, and then we reach a conclusion. And knowing, with our knowledge of how logic and logical variables work, like implications. So let's say we're typically trying to prove a hypothesis of the form P implies Q, or maybe P and then the biconditional. So P is true if and only if Q is true, right? These are basically the two kinds of things that we'll be proving. And so if you can break down the statement that you're given in natural language into P and Q and identify which kind of implication are you using, then that can help give you an idea of where to start. And then the method of direct or contradiction or contrapositive gives us where do we start and how do we work our way to the conclusion. All right, so a direct proof let's assume we're doing just P implies Q. So we're given some statements. If we can write it in the form of P implies Q, then the basic idea is we assume P is true and go through the implications of that. What does P being true mean? Maybe we do algebra, and then we get to Q must be true. So this is, it's called direct because like we start with assuming P is true, and then we get to the point where Q is true. So it's direct. We're going from P to Q. Let's talk about them all kind of in general. So the contradiction. I always mess up the words contradiction and contrapositive. It's clear in my head, but sometimes I mess it up when I say it out loud. Contradiction is if we're assuming P implies Q, then contradiction, the strategy is to assume that P is true and not Q is true. And so assuming that, okay, so here's where we're starting, and I'm going to assume that our destination is not like, I'm going to negate our destination. And so say that both P and not Q are both true. And then this is usually like, we assume this is also called like ad absurdum, where we assume something and then we reach this like crazy pants conclusion. And once we get there, then we're like, okay, this must not have been true. So therefore, our original implication must be true. So we reach a point of contradiction where one of these ends up not being true. And therefore, we get the conclusion that our original implication must be true. So that's proof by contradiction. Proof by contrapositive is if we're proving P implies Q, remember we talked about like the inverse, the converse, and so on, where contrapositive is not, we negate each side and we flip it. So this is not Q implies not P. And we showed with the truth table that the contrapositive is logically equivalent to the implication, right? So these two are doing the same thing. And so this is an indirect proof where we can prove the contrapositive instead of the implication. And so this is where we assume not Q, and then it has the form of a direct proof, where we work our way to the negation of the hypothesis. So that's the contrapositive. Let's look at examples. Before we look at examples, any questions? Right. So there's an implied we know that the contrapositive and the implication are logically equivalent. So since so we've proven it in class with the truth table, and so we know it, and then now we can assume that everyone else knows it. And so if you do this and then you get to not P it being true, then you can be like, great, we're done. Other questions? All right. I think contradiction especially may seem like it's not supposed to work, but let's look at an example. All right, let's look at a direct proof where we want to prove the sum of an even integer and an odd integer is odd. So this is not immediately an implication. Talk with your neighbors. How do we rewrite this in terms of P and Q? And so then we have this like P implies Q format. Talk about it. Go. All right. What do you think P is? Yeah. And then Q is, yeah, the sum is odd. Right. And so we can take this maybe a step further, and I sense that maybe we were gonna need to do some algebra here. And so we could say like if we have one be an even number, so let's say X is even, and then Y is odd. And so that can be, here's where we start. We start with an even number and an odd number. And then we say X plus Y is odd. Right? So we're breaking down this natural language that we've gotten into something that we can actually do work with. So prove the sum of an even integer and an odd integer is odd. So the difference from what I have over here to what you have, you've got some in your hypothesis, which I think is okay. Q, the meat of that proposition is the conclusion that the sum is odd. And so when you're doing this, you don't necessarily need to show this part. So on your homework, I don't necessarily need to show it. Like, I don't need to see it. That's more so for you, like on your scratch paper, trying to deconstruct the problem. And so what I really need is the actual proof. And so again, so proofs are best when concise and complete. And those two things are very difficult to do together, especially when you're learning proofs. So as you practice, start by writing everything you can think of, like every logical step that you think may require explanation. And then on your homework, if I'm like, yeah, I can infer that, then I'll write it down. I'll maybe cross out the lines you wrote, but I won't grade you down if it all logically follows. And so that's more of practice for you of here's all the things I think you need to know. And then I'll be like, okay, I can assume that, I can assume that. And that helps like with the revision process, right? Because we're writing proofs. And so we have one version and that may do the job, but we'll need to revise later on. Okay, all that to say, so we're assuming that, let's say, we'll call them X and Y. So we'll say let X be an even integer and Y is an odd integer. And then we know that an even integer looks like, so even form looks like X is equal to 2k, where k is an integer. An odd number has the form y is equal to 2, well, let's use a different number, 2j, that's not a t, that should be a plus, 2j plus 1, where j is also an integer, right? This stuff isn't new, we're just writing it down. And so far we said X is even, Y is odd. That's our premise. And now we're maybe explaining a little bit of here's what that means. So here's what an odd number means. Here's what an even number means. And then once we do that, now we can substitute it together. So this is where the book's saying like we need complete sentences. This is something that I'll start to look for in your proofs, where if I just went directly into X plus Y is equal to 2K plus 2J plus 1, and like if I didn't have that, then it feels a little bit like an incomplete sentence, right? You've gone from an odd number has the form y equals 2j plus 1. Here's some math. But like that's jarring as a reader. And so if you say like, even if it's one word of like, we're substituting this. And so like substituting maybe like, and adding X plus Y together, like some transitional sentence to say, here's what I'm doing next, and then you show that you're doing it. And then you can actually do the proof part, where we've got 2k plus 2j plus 1, and then note that we're not saying anything about like there being a 2 plus 1 or something. We're not doing that because that's assuming what we're trying to prove. We're just saying we add them together, here's what we get. And so obviously we can factor a 2 out, and so we have 2 times k plus j, and then we've got an extra 1 here. And then we can say the book has an additional measure of like closure of the integers ensures under addition that k plus j is in z. So like you can have a sentence that says that. That seems a bit much even for me. So if you want to have that, like it's not wrong to say that. But we get to something, and so now we say like this is the form of an odd number. And so you could say like, which is odd, or this is the form of an odd number. Like you could say either of those. Just having words to say, being able to point to it and say, that looks like it's odd. So again, having these like interstitial words to explain what's going on. So that way it's not like, here's what I'm assuming, math, I'm done. Having words to explain. And so we get to a point where we say this is odd, and then we can say therefore, and then some sentence to show that we did it. And so the book says, thus, by definition, x plus y is an odd integer. I might say, therefore, x plus y is odd, right? Just some summary sentence to say, yes, we really did it. And then we have QED. All right. We may not have time. Okay, we've got 2 minutes. Let's see if we can do contradiction. Before we do that, any questions on direct? Great. So contradiction, so this is prove that if the sum of a real number and itself equals itself, then the number must be 0. And so the way that the book says is if we have some statement A of x saying that this means we add some number to itself and we get itself back. We've got B which says that x must be 0. So writing it in symbols. And then the logical way to represent this is for all x in the real numbers, if we assume A of x, then we must get B of x as a result. And so the notion of contradiction is we want to assume A and not B. So that's where we'll start. So we'll resume with this on, what is it, Wednesday? We'll resume with this on Friday. And I'm still grading the exams, still grading the homeworks. Homework, was it 4, will be due on Friday. And that's just, you just type up like the problems that appear in the textbook, since I've still got your solutions. Um, I was thinking about this. Print it out and bring it in. Since it's your first LaTeX assignment, maybe. Okay, so okay, I'm making a decision on the fly. For future assignments, it'll just be the printed version, but since this is your first LaTeX assignment, I'll have you zip the overleaf document. So if I'm over here and I've typed stuff in this document, I can go to menu and I can just download the source. And so I can like zip that and save that. And then that zip file you can just upload to Canvas. So I'll change Canvas. So for the first assignment, download the zip file and then upload that. Thank you. I will see you on Friday.